Thank you for attending RSA webinar today. My name is Artur Kosakowski and I will be running today's presentation together with my colleague Rafał Gawenda. The topic of this webinar is RC design, workflows for beams, columns and foundations for columns reinforcement design. You can find information about our new series of robot webinars under these links. Let me remind you about the concept of RSA webinars. We will focus on one or several topics in order to discuss issues frequently submitted to the support team. We will begin with the general introduction of selected features of the program and develop these subjects further based on the feedback we receive from you after each of the presentations. Please mind that these webinars are not supposed to be training sessions. In this webinar, we will focus on design of concrete beams and columns, as well as isolated and continuous foundations under columns. We'll cover the way to create a model which matches the requirements of the RC design modules of robot, get you familiar with the definition of loads and load combinations, and finally discuss the definition of parameters which govern design of reinforcement mentioned before types of elements. For the next webinar, we will focus on the remaining RC design modules of robot. Regardless of a kind of a RC structure you design, it is extremely important that you create its model in a manner that allows you to design reinforcement for each of its elements. The most important is to use the section types which are supported in the RC design modules. And these sections are presented on the currently displayed slide. I'd like to focus your attention that in Robot 2016 you can assign concrete grade to the defined cross-sections directly in the new section dialog. I'd like to remind you that RC member required reinforcement and RC beams design modules recognize elements in different ways. Therefore, you should define multi-span beams as separated bars for each of the span for the prior one, whereas you can define them as a chain of smaller elements within one span, with the possibility of using different cross-sections, or as a one bar when you intend to export them to the latter. Let me show that on my model. Okay, I defined horizontal element as a spread footing. Okay. This is defined as a single continuous element because the design of the continuous footing is not supported in the RC member required reinforcement module. But I defined the beams a couple of them are displayed as a separate elements for each of the spans. Mind that I-shape beams can only be designed in the RC member required reinforcement module. RC columns, which you intend to design reinforcement for, should be entered as single elements between level stories. This allows for correct definition of their buckling length coefficients. Let me show a couple of RC columns defined in my model. Okay. As you can see, all of them I entered as a single elements rather than continuous elements to the entire height of the building. It is not recommended to use vertical offsets for RC beams you want to design reinforcement for, as the offset influence values of internal forces causes large increase of axial force, tension, and significant reduction of bending moment. The same applies to columns. Do not offset them, for example, to align them with faces of walls, as in this case you will get additional bending. So if we look back at the model, Okay, and these columns here, they do not have any offset defined, and even though there is no wall, that would cause additional bending due to the offset from the supported node. The proposed way of designing a T-shaped concrete beam is described in the steps visible on the currently displayed slide. As you can see, instead of defining a T-shaped beam, you replace it with a rectangular one with artificially increased moment of inertia so that you have correct distribution of loads to the beam. Let me show the end of the process on the next slide. After running static analysis of a model, you export the beam to the RC beam design module where you change the beam's cross-section back to T-shape. I'll show you this on the example in a moment. Curved beams need to be approximated by chains of smaller straight elements. Then you can use RC member required reinforcement module to calculate necessary amount of reinforcement. Mind to set the support width to zeros for all but outer elements. In Robot, there is no automatic pattern loading generation for a model, therefore you need to define live loads for each of spans of a continuous beam as separate load cases. Then you can use automatic generation of code or manual combinations to have all possible schemes of load created. Mind that for multi-story building, you may want to group live loads to avoid excessive number of automatic combinations. Mind that pattern loading is done for RC beams defined in the RC beam design module itself. You should define all required types of combinations, and as this is how the RC design modules assign them for particular types of verifications, such as seismic provisions or check for deflections. For example, SLS quasi-permanent combination types for EC2. The ways of generation of both automatic code and manual combinations were covered during our previous webinar for steel design. So please refer to the recording of this webinar in case you want to see how this is done. To design provided reinforcement in a beam, you need to first select in the model and then press the icon marked in yellow on the currently displayed slide. You can either import the results of simple load cases or allow the program to generate automatic code combination inside the design module. You can also import manual combinations already defined in the model instead. So let me go to my model and I will select two beams, or actually one continuous beam. Okay, let's see it in the model. And, well, I mentioned that we return to the design of the T-shaped beams. So let's make the assumption that this first shorter beam span is rectangular, the other is T-shaped. So I will open that in a new window and I will display the shapes that I assigned to these elements. Okay, maybe we will add. Okay, that's T20 by 35, we can see the name. And if I have a look at the definition, you can see that the longer span is a T-shape, which is modeled as a rectangular beam with increased moment of inertia. Right, so let me select these beams. I will export them to the RC design module, RC beams design module. Okay, I will import simple load cases. I switch off simplified names so that I can see the numbers of bars from the model. A Okay, if I have a look at the model again, you can see that actually the shorter span is displayed as the first, the longer span is displayed as the second. So if you want to have the similar display in the RC design module after importing the beam, you may press the change orientation button. And well, remember that actually the longer span is a T-shape, so I'm going to finish my process by applying T-shape section. Well, let me change the height. This is to show you that if you have multi-span beams, you may actually change the arrangement of the spans depending of your real situation in a project. Okay, let me go back to the presentation. While exporting a beam from a model to the design module, you should check the automatic detection of supports. At this stage, you may decide if adjoining beams should be treated as supports and make sure that only these columns of walls that are defined below the beam are selected as supports. For RC member required reinforcement, might to set the correct support sizes in the member type assigned to bars of a model. So if we look at my model, if I go back to the geometry of the structure, I'll select a couple of beams again. Okay, so we have the beam that is defined under a wall, and I would like to focus your attention on this panel here, which is not in the line of the beam. And when we export that to the RC design module, looking at the detection of the support, I can clearly see that that was marked as a support. Okay, in case this is excessive, you switch it off, and then the beam is imported only with the elements that should be treated as supports. Right, so we have 4 supports instead of 5. Let me go back to the model, and now I will select another beam. Okay, this is the beam that is in line of walls and is defined to the edges of the wall. If we go to its properties, we can see that the free span length is 6.21 meter, and if I export that to the RC beams design module, I've got the chance to adjust the supports after the import. Okay, so you can see that by default the span is 6.6, which is to the center of the supports. So as my supports are walls, I can actually put any width I want to. For example, half a meter. You may type the entire length of the wall if you need. And then if we go to the advanced, we just shift the supports by half of their defined width. And by doing so, we have our 621 between the edges of the wall. The RC continuous footing module in robot is based on the RC beam design one, therefore it is intended for design strap foundations are the columns rather than walls. The supported cross sections are rectangles and reverse T-shapes, and to export an element from a model to RC continuous footing module, it is necessary to both set the structure type of the element as bar and define elastic soil under it. So in my model, if I go back to geometry, I make the selection of the continuous footing that I defined, and I will also select 3 columns defined on top of it. And now let me switch off the display of the sections, And what I'm going to do, I'm going to show you first of all the elastic ground definition. And you can focus on the value. That's not the one that is defined, so we can delete the labels that are not used in the model. That's actually my definition with the elasticity values, as you can see it. And then if I select this element, right, you can see that the structure object is set as bar to prevent export of this element to the RC beam design. And then if I press the export button, you can see in the soil parameters that we have exactly the same elasticity coefficients taken from the model. We will discuss the design of the foundations and the walls during our next webinars. RC columns are exported from a model in the same way as beams, but it is possible, similarly to the group design, the steel design module, to calculate identical reinforcement for a group of RC columns which have the same geometry, and this is done by marking the grouping according to the geometry checkbox. So if I go back to my model, I can go to geometry, and I should have a viewer opened with my columns. So if I mark the columns and I export it to the RC column design module, I can mark this grouping according to geometry. Okay, and now if we look at the loads, you can see that we have 3 different groups of loads for each of the columns separately imported, and all these groups of loads will be used to design reinforcement. So we'll have the same identical reinforcement for all 3 columns. If I go back to the model, and I repeat the same operation, the selection of the columns, but this time I will switch off grouping. I will have 3 separate columns imported, and this time I will have only 1 set of loads for each of them. Therefore, the reinforcement for each of them, of course, will be different. Before you start designing a spread footing, make sure that the orientation of the columns matches with directions of supports. If this is not true, you may need to redefine a support applying the required angle of rotation. So let me see what this means. Again, if we go to the model and we select supported nodes, and we will select the column defined on top of it, 3, 6, 7. Okay, I'll try to open that in a new window. Okay, I will switch off the display of the section shape, but I will display local coordinate system of the column as well as the coordinate systems or directions of supports. Okay, and when we look from the top, we can see that they do not match. Therefore, what should be done before the design of the spread footing is the definition of the support which matches the orientation of the column. Then, okay, that's the angle of rotation. And this support should be applied to the node. Okay, so now you can see that this is the same. We have the same directions, and you can check the rotation of the column after selecting the column in the model. You have in the inspector the value of rotation for this section. Okay. To design a spread footing, you select supported nodes and export the values of reactions to the foundation module. You can group the supports to design identical foundations as we did for columns, or design spread footings individually. In my model, there are significantly different loads for each of the foundation, therefore I'm going to design them separately. I'll switch off grouping, but I want to define the same soil conditions for all of them. So by applying the angular rotation to the support, I changed the status of the results. So let me reload the model, which is saved with the results. And let me also show how you can work with the selections dialog. So I want to select all the supports under the column. So I select first all the supports, then I select all the bars and I make the common part with the previous selection. And finally, I will select all the columns that are defined on the top of the selected nodes. So you can see I've got all the columns that are defined over the supports opened in a new window. And then I will deselect all the bars, none. So I have only supported nodes selected. I can export them to the design module. I will switch off grouping. Okay, so we have all the foundations imported. I will select one of them. Then I will go to the soil definition. I will create some layers. And I will save that under name soil layers. Okay, I'll close this dialog, and now I will select all the foundations, and in the inspector I will select the soil layers parameters so that I can design these foundations for the same soil conditions. Okay, let me go back to the slides. It is also possible to design a foundation for two columns. Let me show that on the example. So I will go back to robot, switch to the geometry layout, and this time I'm going to select two supported nodes, 338 and 8039. I will add the selection of the bars by selected nodes. No, okay, close the dialog. None, and I will select nodes. Okay, only two bars, right? So we have the situation like here. I will switch off the display of the cross sections, and I will switch off the selection of bars. And then when I export these two nodes, supported nodes, to the design module, I can answer yes for the question about the designing common foundation for both of them. And we can see that we have a foundation and we have two columns that we imported from the model. The important thing is that you should have the coordinate system of the columns being aligned. So let me go back to my model, and if we look at the columns and we display the coordinate system, you can see that they're actually pointing in the same direction. Let's look at the RC member required reinforcement module now. This module is in fact similar in principle to the steel design one, which we covered during our previous webinar. Calculations of reinforcement are done in a number of specified points and are based on a set of parameters assigned to elements of a model. The results are available both in the table and as diagrams. Let me show this design process on my sample model. So I will switch to the layout for RC member required reinforcement. You can see that I have the type and parameters assigned to all these elements. And again, you can see that this, as I mentioned, it is important to define all the types of the combinations in the model. And then I reduce the number of points just to speed up the calculation process. And in this way, you can roughly estimate the amount of reinforcement necessary for all the model and make the decision whether you want to increase or decrease some section size before, for example, going to the detailed reinforcement arrangement in the provided reinforcement modules. I'll skip the warnings and errors for a moment. We'll return to that dialog later on. But as I mentioned, the results are available in the table for beams, columns, okay? If there is some issue with the design, this is marked in the table. And also the results are available as diagrams. So if I select all the bars and I open them in a new window, I can go to the diagrams and, for example, display the value of required area of reinforcement. By default, an RC beam is designed against the simple bending and it is designed in the specified number of points. But you have to remember that you may need to include other internal forces necessary for reinforcement calculations, such as torsion or axial force. And mind that the settings, the default settings for beams in the provided reinforcement and required reinforcement is different. In addition, it is possible to decide if you want to design reinforcement for shear in the center of the support and at the edge of the support. Let me show this on the sample beam from my model. Okay, so let's go back to the geometry. I will select another beam and I will export it to the RC beams module. This time I want to display the full names of the supports to understand which support is a column, which support is a wall. And by default, the supports are set as concrete, meaning that the values of forces from the model are taken at the faces of the support, 30 centimeters, 20 centimeters. But if we go to the geometry of the beam, we may actually say that the wall is masonry. And if we look at the diagrams now, we can see that the left value is as previously from the middle of the support, the right value from the face of the support, of course, and the right value is from the middle of the support. And when we let me show another slide before I move on. In addition to the decision on the support type, you may also decide how to arrange stirrups at the locations of the supports. So depending on whether you have concrete or masonry supports, you may have a different reinforcement arrangement. And if we go back to our beam, if I now calculate reinforcement, there will be the information about incorrect arrangement of stirrups for the right support, which is masonry. And to deal with that, we may go to the transversal reinforcement tab, go to support reinforcement, and tell, okay, for masonry, I want to have the reinforcement, shear reinforcement stirrup generated across the support width. And if we look at the reinforcement, you can see that there's left side support where there is a column, there are no stirrups, but there are stirrups generated on top of the wall support. In case you need some additional beam's capacity, you may include assembly reinforcement in calculations. Mind that you have to set its steel grade as being the same as set for main reinforcement bars. How this works: if we go again to my model, if I select another beam, okay, that's the 2-span beam. I will export that to the RC Beams design module. Okay, you can see that if you do not pay the attention to the supports, you may actually have something which is a bit surprising. So let me go back to the structure. I will repeat this export, and this time I look at the supports, and what I have to do, I need to switch off this checkbox and mark the last one. And now it is a bit better. Okay, let me calculate the beam with the default parameters. And when we look at the reinforcement, we may see that we have the situation when we have assembly bars overlapping with the main bars. But if we go to the reinforcement pattern, you may tell the software, okay, consider my assembly reinforcement in the calculations of beam capacity. And if we repeat the calculations, okay, we have only single bar in this location. And we have a separated bars because our reinforcement pattern is set as single span. When we mark whole beam, we may have continuous bars generated. Using diagrams tab, you can check the results along the beam to find out what to correct when there are errors reported during the design process. Depending on the calculation options, you can see the results for envelope of internal forces, default for simple bending, or each of the combinations separately, default when you include axial forces. So if I go back to the model, we switch to the diagram, you can see that there is only envelope because the calculations were done for simple bending. If I go to the design options, if I include axial forces and I recalculate the beam, you can see now that we have quite a number of combinations, and we can look at the values of the results for each of them. Okay. Using diagrams, you can also check the safety margin for generated reinforcement and decide if it should be redesigned with different settings of reinforcement pattern or if you need to manually edit some rebars. You can see the values along the beam by placing mouse on the diagram and moving it horizontally. And these values can be seen for the entire beam, or you may switch to display to a single span and navigate through the spans. Let's focus on the RC columns now. Mind to set the correct buckling parameters for these columns. The best is to do so in a model so that they are coherent for both RC member required reinforcement and RC column design modules. Remember to check what kind of internal forces and verifications are set for the design of a column, as they may not be included in the default settings, or you may want to exclude some of them. Let me show how this works. Okay, all right. So I will go back to the geometry of the model. I will select one of the columns. Okay, this is the column defined at the end of the wall. So, okay, if I display local coordinate system of this column, I may say that, okay, that I'm not concerned about the backlinks in MY, but I also want to design this column for unidirectional bending MZ. So if I go to the member type, I will actually change the parameters for backlink, and I will give it a new name, and I will apply the set parameters to my column. And then if I export that column to the RC columns design module, I should have the same parameters here, which is switched off, which is 1. That's okay. That's as I defined them. And also in the calculation parameters, I want to include bending, and I want to design that for one direction, unidirectional bending only. Okay, let me calculate that. And again, I defined some seismic loads in my model which were imported, and there is the warning that, okay, you want to include seismic combinations, but actually you haven't marked this in the parameters of the calculation. So let me mark seismic dispositions, and this time I should have no warning about that. The only warning is that it is the information that I excluded bending in one direction, which is okay. And then if we okay, let me show another slide. You can check the column's capacity by looking at the interaction diagrams for each of the combinations, right? This is what is shown here. And if we look at the model, we can see this, and you can see that the column size is overestimated, right? So we may redesign that column. We may change the cross-section in the RC column design module. I will put that 20 by 20 centimeters. I will recalculate, and this time I've got the error because actually the seismic parameters does not allow for the column smaller than 25 by 25 centimeters. I will ignore that. Of course, I could increase the column size of the column again, but instead, okay, it's a bit better for the capacity, but instead I'm going to go to the reinforcement, to the results, and then I can update the model with the cross sections that I designed, I changed in the RC columns design module. So if I press structure update, this 20 by 20 column should appear in the model, okay? And you can see, yeah, this is the change in the cross section. And then I will reload the model. Because again I changed the status of the results, and I will show you next slide. Designing spread footings, you should remember not only to define soil layers, but to set required design parameters in the geotechnical options. So if we look at the model, I will select one of the supported nodes, and I will export that to the RC spread footing module. Okay. And I will go to the soil, and as I saved the layer, I can invoke that. Press the apply button. So we have the soil parameters that I defined, the soil conditions under the building. And also I will go to the geotechnical options and, for example, change the calculation method to laboratory. I will calculate. Okay, the same, seismic dispositions, no requirements. Okay, so we go to the parameters, we mark that checkbox, we redesign. Okay, so we have the small size of the foundations determined by the program. Let me show another slide. And you can access the results for geotechnical combinations such as stress in soil by placing mouse over the one of the results viewers. And this is how it is done. I mean, okay, we've switched to the results. We can press, for example, on the capacity, which selects the governing combination. When I click on the viewer, we can see the stress level. And the same, we can identify the governing combinations for contact surfaces, stability, rotation. If I go back to the presentation, and I'll show you the next slide, and you can see that you can access the results of reinforcement by clicking on the combination with the mark with the stars. And if we do so in our model, yeah, for example, this one, we can see the punching parameter. We can click on the punching shear to find out which is the governing combination, and also we can see the information about the reinforcement calculated for each of the directions. Let me now indicate, based on our experience, the most typical common mistakes. They include non-member types of reinforcement parameters assigned to bars, which results in error during required reinforcement calculations, attempt to squeeze U-shaped anchor loops in a very narrow beams, use of steel cross-section with manually changed material to concrete for reinforcement design, which of course doesn't work, and design of reinforcement having only ULS or SLS combinations defined. Let me introduce a couple of useful options that you may not be aware of. You can access the already designed RC elements by double-clicking on their names in the RC inspector. When you change values of loads in the model, you can update loads in already designed RC elements rather than delete it and import it from a model again. This allows you not only for design of new reinforcement for increased values of internal forces, but for verification of already existing loads as well. In case you find out that you need to increase section size to be able to design an RC element, you can update the model directly from the RC design module, which we did a moment ago. Starting from Robot 2016, you can identify reinforcement bars that needs to be altered by pressing Select Reverse button from the Calculation Errors dialog. I promise you that we return to errors and warnings from RC member required reinforcement module, and this is the slide that addresses that. As you can see, you can display detailed information about warnings and errors received during calculations of required reinforcement of beams and columns in the remarks columns of the required reinforcement table. Might to switch display of these columns might to display this column on all tabs, beams, columns, and general. It is possible to make manual changes to automatically generated reinforcement. You can edit groups or individual reinforcement bars after selecting them in either in the reinforcement table or on the viewer of the designed element. You can not only change diameter of a selected rebar, but you can move it to a new location, extend or shorten it, as well as redefine hooks. Let me show that on the example. So let me go back to my model. I will go to geometry. I will select another beam. Right. I will export that to the design module. And I will calculate it. Okay. When we go to the reinforcement, we can see that top and left bar are not symmetrical. And as I said, we can adjust that manually. We may select bottom reinforcement bar and change the origin of the bars. Okay, move them right 3 centimeters, and we can do the same for top bars. Move them 2 centimeters left. But you can also set symmetrical reinforcement pattern, and then if you calculate the beam, you will have the symmetrical bars for top and bottom reinforcement. Okay, let me go back to the geometry, the structure view. I will select other beams. Okay, this is 2-span beam. Yep, in the model, I will export that to design module again. I will calculate the reinforcement, and then if we go to reinforcement layout, I may say that, okay, I want to edit my top rebars and I want to tell the anchored in the column below. So I'll go in the properties of the bars to hooks, right hook set as 90, and for example 1 meter, because it is how I want to have this reinforcement arranged. And you can also use set of reinforcement addition tools to manually change the arrangement of generated reinforcement. I'll use one of them to show how to merge 2 separate reinforcement bars into a single one. So if we go back to the beam that we designed, I will select, switch to the detail tab so that I can select a single bar. Okay, I selected 2 separate bottom bars. I go to the reinforcement and then connect reinforcement bars. And now you can see instead of 2 shorter bars, I have 1 longer. It is also possible to redefine distribution of stirrups. For example, move them in case they overlap with some openings defined in the beam. So if we go back to the model, I will define the opening, around opening, for example, for some electricity cables running through the beam. For example, like this. Yes. Okay, so right, that is a situation when my opening is located at the support, at the location of the stirrup. So I'm going to select the stirrups, and on the spacings and areas, I want to move the entire set of stirrups 5 centimeters right. Okay, to avoid this collision. After editing reinforcement, you should freeze it and run the verification. So let me show how it works. If I go to robot, okay, this is this freeze reinforcement, and by default, we have the auto verification, so it means that after I change the position of the stirrups, the beam was verified, there was no errors reported. Okay, it is like pressing this button, no errors reporting. But if I, for example, select one of the stirrups, of course, there will be the information that, okay, now the shear is no longer transferred by the beam. In case you need to add new diameter of reinforcement bars on new steel grade, you should edit the reinforcement bars database. To do so, go to Job Preferences, select the database you want to edit, and open it with the indicated button. The same applies to wire fabrics. Let me finish today's presentation with this last tip. When you notice that the tabs which allow you to navigate inside the RC design model disappeared, you can restore them by opening the layout from template. Seizing the opportunity, I'd like to introduce to you Autodesk Knowledge Network site, where you can find useful articles on the topics covered during this webinar, as well as on many others. I would like to start the question session now. I'm sorry to having a slightly longer presentation today, but I wanted to cover the entire spectrum of the options, so it was, as I said, a bit longer than usual, but feel free to ask questions now.
So thank you, Arthur, for a nice and detailed presentation, and I will start to read some questions which appear on the questions panel on the web GoToWebinar panel. So let's start with this one. Could you please repeat the way you align the coordinate system of the column and its footing?
Yes. Okay, so if we go to geometry, okay, let me find the column. Okay, so for example, we have here the situation that we have a spread footing that is different, I mean, with the coordinates directions different than the column. Okay, so I don't need the wall probably for that, but anyway. So we can display the coordinate system of the column, and we can also display the system of the supports. Okay, where we have supports, right? Detailed system. Oh, sorry, detailed system. Yeah. So we have the column and the spread footing. And if I open that in a new window and I look from the above, that will be easier to see where we are. Okay, so they do not match, obviously. So first of all, I select the column and I can see the gamma, I mean the rotation angle, right? So I'm going to match the rotation of the column with the rotation of the support. So in the definition of the support, when we define the new support, we may press the direction button, and then the first option is the rotation about the vertical axis. And you should just match the rotation of the column with the rotation of the support. I mean, you point the x-axis of the support in the direction that you specify the angle of rotation for. So if I define this support under the column, okay, the direction should match, right? Of course, you may rotate that by additional 90 degrees in case you want to, for example, have x and y in the direction matching with the column. That's of course something that is up to you.
Arthur, there are some questions about generation of RC drawings and showing us all calculation notes, summaries, tables, etc. So, could you please?
Right, so let me select one of the columns and export it to the design module. When we calculate the column, we have the access to the calculation node on the last tab, and here you can see the results of the design, and also you may display the calculation node in a separate viewer. This is generated as RTF, and this is the way to access the calculation node for each of the RC element that you can design in robot, so beams, columns, spread footings, etc. And on the right hand side, in the vertical toolbar, you can find the drawing button, and again it is the same for each of the provided reinforcement modules where you can generate the drawing. And this works for beams, columns, spread footings. Have I managed to answer this question?
I think so. So the questions: Can we see design reinforcement of columns and reinforcement aligned with each other?
Right. There is the way to design the chain of columns, but I think that you may actually look at the also at the option which not this one. So this I need to switch to the RC. Yep. You may see in the reinforcement pattern there is something like a dowel bars when you can specify the connections to the upper column, and you may just define this as the reinforcement that is as for the upper column. So, for example, like this. Yeah, there is also option that when you have the upper column already calculated, you may select that information for the design of the current one. So it makes sense to run the design from top to the bottom of the structure.
So there are some questions about the transferring reinforcement to or from Revit. So the short note is it is possible to transfer, import some calculated reinforcement from the robot to Revit. There are some limitations. For example, it's not possible to import any reinforcement calculated for slabs or walls. and columns are footings and beams are supported, but with some limitations. So there is not 100% full transfer of the reinforcement. Another question about the recording. Yes, as usual, the recording, the session is recorded and will be posted as usual on YouTube, our YouTube channel, and on our playlist. Please expect it to be there in a few days' time. And also we will publish presentation as usual. So as I can see, there are no more questions related to our today topic of webinar. So if you have any other questions, please report them, post them on our forum, and we will be happy to answer you. And for now, thank you again for attending the webinar. Thank you, Artur, for detailed presentations, and see you next time for next webinar. Thank you.
Thank you.